Hi everyone, in today's video we are working on task 2.6, so we are on page 35 of your packet. If you're not there yet, go ahead and flip to page 35. The focus of today's task is to practice our graphing of linear functions. We're going to be going from equations today, and then we are also going to work on using our properties of operations to see if expressions are equivalent to each other or not. Alright, so the first thing that we're going to look at is three different students' work and kind of compare them to each other and see what we noticed. So on an assignment, Michael, Scotty, and Dennis are asked to complete the following task: to write a linear equation for a line that passes through the points -2, -6, and 4, 3. So they each created an equation for that line, and they all got different answers. So Michael, he got his equation was y equals -6 plus 3 over 2 times x plus 2. Scotty got y equals 3 over 2 times x minus 4 plus 3. And then Dennis got y equals 3 over 2x minus 3. So these are three different equations for the same line. So you're a bit confused on how they got such different solutions for this. So let's investigate which one of them is correct. So to do this, we're going to graph all three of them on our coordinate plane here. So we're going to use different colors to do this, and I already kind of separated them here. So we will show Michael's answer in blue, Scotty's in this pinkish red, and then Dennis in purple. So let's just take it one at a time. We can start with graphing Michael's equation. So what is the important information or key features from Michael's equation? So what's our starting point in this one? Good, so our starting point is -2. Remember, it's opposite of what's added or subtracted inside of our parentheses with x. So since it's +2, our x is going to be -2. Our y is by itself out front, that -6. So -2, -6 for Michael's starting point. His slope is multiplied by those parentheses, which is 3 over 2. Alright, so let's go ahead and graph Michael's line. So we have a starting point of -6, -2 down here. Or sorry, -2, -6. That is our starting point for Michael's line. And then we're using our rise over run. So up 3, right 2 puts us right here. I'm going to keep using this pattern, up 3, right 2, until I fill all my graph paper. Up 3 and right 2. Alright, that's as far as I can go in this direction. So let's go back to our starting point and go the opposite way. So down 3, left 2 now. That'll put us right here. And now we can connect all of our points here. So again, you want to make this a straight line going through each of these points. Alright, so there is the line for Michael's equation. I'm going to go ahead and erase my rise over run steps just because we're going to graph all three lines here, so it's going to get a little bit messy. Alright, the next one we're going to look at is Scotty's equation. So what is our starting point from Scotty's equation? Good, this one's going to be 4, 3, and our slope for Scotty's, again, is multiplied by those parentheses, which is 3 over 2. So we'll start at the point 4, 3. So 4 for my x, 3 for my y will put us about here. And then we are going up by 3 to the right by 2. So up 3, right 2, up 3, right 2. I'm going to kind of circle around those blue points so we can see that they're still in blue. And I got as far as I could at going that direction, so let's do the opposite. So down 3, down 3, left 2 will put us right here. Down 3, left 2 again, right here. Down 3, left 2, down 3, left 2. Alright, and that is as many points as we can fit for Scotty, so let's go ahead and connect our points. I'm going to try to show it next to our blue line here. Alright, so now we've graphed Michael's and Scotty's equations, so we only have Dennis's left. Alright, so let's take a look back at his equation. What's our starting point? Well, you might notice, again, we don't have anything in parentheses with x, so this is actually our slope-intercept form, and since there's nothing with x with x in parentheses, that just means our starting x value is actually 0, so this gives us our y-intercept. And then our y value to start is -3. That's far away from the x over here on the right. All right, and our slope, again, that's always multiplied by where your x is, so our slope is 3/2. Okay, so let's start at our y-intercept at 0, -3 here, and then we're going to use our slope again. So up 3, right 2, up 3, right 2, up 3, right 2, because that's our slope here, and then up 3, right 2, as far as I can go in this direction. So let's go again from our y-intercept here. We're going in the opposite direction, so down 3, left 2 here, down 3, left 2. All right, so those are all of our points for Dennis's equation, so let's connect these points here. Again, I'm kind of showing that we're going next to our other lines, just so we can see all 3 of those colors. Okay, so now we've graphed all 3 of these equations. So what do you notice about these graphs from these equations? Yeah, hopefully you see that they're kind of all the same, right? They're all on top of each other. They have the same points for each of those equations. So what do you notice about the equations? What was similar, what was different about Michael, Scotty's, and Dennis's equation? So one thing you might have seen is that all of them have a slope of 3/2. And we saw that when we were graphing on our coordinate plane, and we see that in our equations. They all have a slope of 3/2. So their graphs are the same, they have the same slope, and they have the same points. So whose equation is correct? It's actually going to be all of them. So all 3 are actually correct. We can see again they all had each other's starting points here. So Michael's starting point was -2, -6, so we have all 3 of those colors down there. Scotty's was 4, 3, all 3 of those colors are at this point here, and then Dennis's y-intercept was 0, -3, and they all graphed that y-intercept at 0, -3. So these equations all graphed our same line for this equation. So that means that these equations are actually all the same. They're all equivalent to each other. So let's take a look at how we prove this algebraically. So using algebra, how could we prove those equations are the same? Well, here are our equations again. So we're going to use what we know about distributing and what we know about combining like terms to simplify the right side of each of these equations and see what we notice. So in Michael's answer, let's start there. We want to simplify his equation. Here on the right side, this expression, so I'm going to distribute this 3/2 to everything inside of parentheses. So that'll give me 3/2 times x plus 3/2 times 2. The -6 out front here doesn't change, so I'm going to drop that down. -6 plus all of that we just distributed, and this is still equal to y. All right, let's simplify this real quick. So we'll have y equals -6 plus 3/2x. We already multiplied that. And then 3/2 times 2, go ahead and plug that in your calculator. You should get 3 for that. This is just like 2/1 times 3/2. Those 2's will cancel out there. Okay, so we get y equals -6 plus 3/2x plus 3. We've distributed everything, so let's combine like terms. What are our like terms in Michael's expression here? Good, we have -6 and +3 because they do not have x's. So this is going to simplify to 3/2x. This doesn't change here, so we drop it down. And then our -6 plus 3 gives us -3, or -3. And then we still have our y equals out in front. All right, so Michael's answer simplifies to this expression down here, or this equation. All right, let's take a look at Scotty's. Again, we're going to start with distributing. So I have that 3/2 times x minus 4 here. So I'll distribute that to both of these terms in parentheses. So 3/2 times x, and then we have plus 3 over 2 times negative 4. Again, I like to put parentheses around what we're multiplying it by, especially when we have those negatives here. It kind of keeps it separated for us. All right, and then we still have a plus 3 at the end. That didn't change. Let's go ahead and simplify this with multiplying our 3 over 2 times negative 4. You should get negative 6. You can plug that in your calculator as well. So negative 6, and then we'll have plus 3 on the end. Again, that doesn't change, so we carry that down. All right, and now all we have to do is combine like terms. So I'm going to add together the negative 6 and positive 3. So those two combine to be negative 3, right? Negative 6 plus 3, and then that 3 over 2 times x does not change. And then this whole time we still had our y equals on the left side. So Scotty's answer simplifies to y equals 3 over 2x minus 3. All right, and take a look at Dennis's answer here. Can we simplify this one any further? Yeah, hopefully you saw there's nothing to distribute here. There's no parentheses, so I don't have to distribute, and these are not like terms. One has an x and one doesn't, so Dennis's answer is actually already simplified. So what do you notice about these 3 expressions that the students created and what they simplified to? Yeah, they all simplified to the same thing. So each one of them is y equals 3 over 2x minus 3. So all 3 of those equations simplified to be the same thing. So when this happens, we actually call them equivalent equations. So all of our beginning equations up here at the top, those are equivalent to each other. They started looking different, but they simplified to the same thing. So those are equivalent. So let's look down here in our little box. We're going to talk about those equivalent expressions, are when we have 2 or more expressions that simplify to be the same expressions. Right, so those give us, when we have that simplifying and we get the same thing, those are equivalent to each other. So that's why Michael, Scotty's, and Dennis's graphs are all the same, right? When we plotted those points, all of those lines are the same because those equations are equivalent to each other. So let's do some practice with finding those equivalent expressions and simplifying. So let's simplify these expressions here to find which ones are equivalent. You can go ahead and pause the video too and give this a try, and then check back to see if you were right. Alright, so in this first one here, we don't have anything to distribute, so we're just going to combine like terms. I have 2x minus 7x. That's going to simplify or combine to negative 5x. And then our other like terms are negative 8 and positive 2. So negative 8 plus 2 gives us negative 6. In this second expression, I'm going to distribute this negative 5 to everything in parentheses. Whoops. So negative 5 times x gives me negative 5x. Negative 5 times positive 1 is going to be negative 5. Alright, and the last one here, we got to be careful to start with our distributing. So I'm going to multiply 6 times x is just 6x. And then 6 times negative 1, this is going to be negative 6. Alright, and then we still have that negative 11x on the outside. That didn't change. Last step we have to do here is combine like terms. So our like terms here are 6x and negative 11x. Those add together to be negative 5x, right? 6 minus 11 is negative 5. We're still multiplying by that x. And then we carry down our negative 6 from this step here. Nothing to combine with that. All right, so then we want to circle the expressions that are equivalent to each other. So which of these expressions simplified to be the same thing? Good, our first one here and our last one. So that would mean that 2x minus 8 minus 7x plus 2 is actually equivalent to 6 times x minus 1 minus 11x. Alright, so that is some practice with finding equivalent expressions. On the next page in your packet, this goes over some practice again to find equivalent expressions. So you can go ahead and work through column A and then check your answers on this. I'll kind of zoom out so you can see all of these. Your expression in column A should simplify to be the same expression in column B. So column A and column B, those are equivalent to each other. So check your work after you simplify to make sure that you get the same expressions that I did in column B. Alright, if you have any questions, feel free to talk to us in class or stop by the Learning Lab.